Yes, okay. So I also changed the title a little bit, and it says now the challenge of determining toxicity from rare earth elements in environmental aquatic samples. And this is based on data and results from a number of people who worked on REE-related issues in my work group. And also, of course, from Chantal and Marion. But please see this mainly as an introduction to the talks that come later on, to give you a bit of a perspective and also to address what others said yesterday. So how do we actually, what's the environmental relevance, and how do we actually say that rare earth elements, or determine that rare earth elements are toxic in the environment? This is an overview, one of these nice maps that Forex Atlas provides with the distribution of, in that case, lanthanum across Europe in stream waters. And it ranges between less than 0.002 to 60 micrograms per liter. The 60 micrograms per liter can become a bit more important later on. See that mostly the concentrations are very low. So it's only this one dot over here which is actually shows increased toxicity, not increased toxicity, increased concentrations, whereby Forex claims that this is still background concentration from geogenic impacts. So. But the questions that need to be asked and preferably answered to this respect is, why should we be interested in measuring retoxicity in environmental samples at all? And how can we know that increased concentrations, if they occur, matter? And of course, we all know that there are anomalies in stream waters. A lot of this work has been done by Michael Bau's group. And he measured increased concentrations of, for example, gadolinium in the Weser, in the Wupper, in the Havel in Berlin, etc., which was mainly due to medical applications, so contrast agents, etc. But we also have lanthanum, samarium, gadolinium, cerium in the Rhine River, and at least lanthanum, samarium, and cerium are not from medical applications, and I'll get to that in a minute. But we also have, for example, neodymium and a couple of others in the Rhine estuary, in the Tagus estuary, and these are mostly from fertilizers or fertilizing plants, at least what people think. And Tepe also from Michael's group, termed then REE 2014 as emerging contaminants. So let's look a little bit onto the Rhine River and these increased concentrations of lanthanum and some other rare earth animals. Rare earth animals is also good. Rare earth metals. So I asked a colleague of mine to come up with a substance flow analysis and look into all these different sources and processes that could lead to increased concentrations in the Rhine River section. And this is quite a nice picture with a lot of gaps. If you would go into the details, we would see that there are a lot of processes we do not know and we can't quantify. But what became very clear was what also Michael Bau already traced these increased concentrations back to, because it's due to the effluence of a company that produces fluid cracking catalysts, which is situated in Worms, directly at the Rhine River. So they emit effluents with concentrations of about 40 milligrams per liter lanthanum per liter into the Rhine River, and I calculated the annual impact, and that adds up over a year to almost 300 kilograms, which I think is quite a lot, but of course there are no threshold limits at the moment, no threshold criterion, so they have the full permission also to do this. This is just an overview of the Rhine, and they are situated on the left bank side. At river kilometer 447. And so they approached us at some time and wanted to know what the toxicity implications of these activities would be, emitting that relatively high concentrated lanthanum into the Rhine. Because they thought that at one moment in time, some threshold criterion might turn up, and they wanted to be free. They wanted to know in advance what they might have to face. So what we did in the course of the cooperation was we also did some plume modeling at low water at two different situations, at low water discharge and at high water discharge, which I'm going to show you in a moment. And at low water discharge, so low water level, low water discharge in the Rhine River, the effluent discharge of the company stayed the same. And at low water discharge of the river, we had a relatively narrow near-field region, meaning very limited zone of strong mixing. So within 4 to 5 meters of the effluents coming in, they were completely mixed vertically in the Rhine River. And here, so here's the surface of the Rhine, here's the sediment, this is the plume. So the contact to the left bank, left river bank, because the plume is, or the effluent, the discharge point is a bit further away from the river bank. The contact to the river bank happened at about 200 meters downstream. During high water discharge, the situation was very different. So this is the surface of the river Rhine at high water discharge conditions. This is where this effluent point is, and due to the high salinity of the effluent, it sinks to the bottom relatively quickly, so it does not contact the water surface over the first kilometers, really, and according to our model, I must say. And then it starts mixing relatively slowly. So the near-field region, when you have the first mixing, vertical mixing, is at 45 meters or 46 meters compared to these 4.5 meters before. So the plume surfaces actually on the river bank, I must say to that, at a distance of 3 kilometers. So when you take samples because you want to inform yourself or others about the impact of the effluents, it might be that everything's fine close to where the effluent is discharged, and only kilometers away, when you take the samples from the side of the river, from the river bank, only kilometers away, it might turn up that you see increased concentrations. But these were two extreme examples, low water discharge and high water discharge. So they also took samples which were analyzed and which they provided to us. And these are now, of course, only average and low water discharge conditions, because during high water discharge, nobody would go there and sample. So the samples were filtered and analyzed by ICP-MS. And what you can assess is that we have very close to the discharge point concentrations of about 30 milligrams per liter or around that. The left river bank, those are the red labels, we got elevated concentrations, the right riverbank. There was nothing happening over that time or that distance that was sampled. So we had, sorry, it was microgram, of course. So we had concentrations up to 30 micrograms per liter. Question is, does it matter if we have these concentrations? We can measure them chemically, but what relevance does it have? So, and that's where we actually get into the field of also risk assessment. So can we say that there's an ecological risk that is involved with this? And when we look into the principal procedure of risk assessment, and I really like this picture because it's so simple and makes it so clear, I think, then we have on one side the biological effects. These are the effects that we see or that we can measure in the laboratory with the bioassays, for example. So we have, for example, we could apply the whole biotest battery to it, have 4 or 5 different species, which we then expose to increasing concentrations of lanthanum, as you did yesterday. And then we come up with something like this. Hopefully, we will see that on Thursday. We will have this nice S-curve. We will have we can put the concentration as logarithms and the percent effect, for example, inhibition compared to a control on the y-axis. And then we could deduce, if all goes well, the LC50 or the EC50 here. So the effect concentration, which causes 50% of the effect or of the inhibition. Coming back to this picture, that means that this more or less reflects what you just saw in the other picture. So we have concentrations which cause, or we have very low concentrations and we have very high concentrations which cause an effect. And then we can compare it with a chemical contamination. And if there's an overlap, simply speaking, we can think of it as being a potential effect that could occur. Now that sounds very easy, is too easy because it's not that simple. So we have to go a little bit back into this S-curve and what I said yesterday about this no observed effect concentration, which is, let me just go back, which is the highest concentration which does not yet cause an effect, while the LOEC is the first concentration which causes an effect. So, and in principle, you would narrow your experiments, the concentrations that you apply in your experiments, you would narrow them. You would always try to get to the point where you, at one point, at one concentration, do not have an effect, and the next concentration there is one, and then you would have a good idea of the NOEC and the LOEC. Of course, the NOEC that is measured just by one or with one species or determined just by one species does probably not have a lot of information. So perhaps this species is especially sensitive, or your bioassay is especially sensitive, or you measure at a pH in which it's especially available or whatever. Or the other way around, which would even be more difficult if your species is less sensitive. So you would derive, or you would get an idea that everything is fine, only because your test species does not react to the specific compound, like, for example, lanthanum, while a lot of species in the environment do. So that would be a situation which you would not like to have. So That's the reason why the NOEC values, in order to derive an environmental criterion, which is actually this part where you would think this is where the effects start, the NOEC is divided by an assessment factor, and then you get the predicted no effect concentration, this PNEC. So the PNEC is often used as a threshold criterion, which shows also by the European Commission as a criterion above which there may be a risk. This is set in a big document, the TGD, the Technical Guidance Document from 2003, in which the assessment factors are detailed. And the assessment factors change depending on the quality of the information on your databases, basically. And they account for the variability of toxicity data. So the results that your lab gets compared to another lab, which may differ, if you repeat the tests a year later, it may differ. We always work with living organisms. So there is a certain variability involved, even though we try to keep track on any changes of sensitivity or adaptation or whatever. So then this assessment factor accounts for intra and interspecies variation. So meaning, my example from just a few minutes ago, you have a species, you measure, it has a certain sensitivity, and then the organisms out there might be much more sensitive than your test species, which you have in the lab, like your Caenorhabditis or the algae or whatever. So that's also where this is, which this assessment factor should take account of. And then the short to long-term extrapolation. So most of the tests in the lab are short-term, are acute. What we actually look at are long-term change, or what we need to face are long-term changes in the environment. So that's also something which is incorporated into this assessment factor. And then that's the laboratory data to field impact extrapolation. And this is mixture toxicity. This is toxicity, secondary poisoning, the contaminants are taken up and are accumulated, and then somebody else comes and eats this algae, for example, the definite. The definite eats the algae has taken up a lot of contaminants, then the definite has them. Then the definite is eaten by a fish, then the fish is eaten by us, for example. So that's also something that this assessment factor tries to take up. So they range from 1 to 1,000, depending on how many data on toxicity, from how many species are available. And this is now actually directly taken from this TGD. And here you see, or you get an overview over the available data, the different cases by which you have to decide what assessment factor you can use. And so if you have at least one short-term LC50 or EC50 from each of 3 trophic levels of the base sets, which means fish and Daphnia and algae, then you still have an assessment factor of 1,000. And the better your database is, the lower your assessment factor gets. So until you get up to a species sensitivity distribution, which was mentioned also by Antonios before and published by some of you already for the REE elements, then the assessment factor would be something from 1 to 5. Now perhaps it sounds a bit strange how they arrive these assessment factors. 1,000, 150, 10, 5, or 1 to 5. How can they actually determine this? And they can't, of course, not. So this is something that a work group that came together decided upon. So it's a scientific, political decision to use these factors. Nobody can actually account for all these different conditions. But they said, well, to be on the safe side, if we don't know that much, let's say 1,000, something like this. So this has to be kept in mind when we look at threshold environmental quality criteria. So if we had measured an EC50 value of 4 milligrams per liter in 1 out of 3 species, and you always take the lowest EC50 or NOEC value that you find in publications or in reports or scientific data, it can be confirmed that these are of high quality and followed a number of conditions that they provided measured concentration, or that they provided the controls, or that they use negative, positive controls, etc. So a number of criteria for that as well, and then you can use these data to derive a PNEC. So with an EC, let's say we have the first case here, and you would derive an EC50 value of 4 milligrams per liter in 1 out of 3 species. Then the PNEC would be 4 micrograms per liter, which is pretty low, of course. And it can easily happen that your derived PNEC value is far below the background concentration. And then you think, something may be not really reasonable. So, when we look at this, we tried to derive already in, I think, 2016, we tried to derive PNEC value for lanthanum in water, looking at all those publications which at that time fulfilled these criteria for being of high scientific quality, and we came up with we suggested a PNEC value of 4 micrograms per liter because of studies which showed relatively, or I think that was, 40 micrograms per liter, and then we used an assessment factor of 10, if I remember correctly. So that was the threshold criterion. When we now look into the data that Grace, so this company, provide us with, so this would be the PNEC. The Rhine water and Worms had concentrations up to, that's what they measured at the time, 60 micrograms per liter. So this would provide an environmental risk. But is this overprotective or underprotective? That's a big question, because these threshold criteria, and you might have deduced that yourself already, are a construct. And when we look at other metals, how they are dealt with, then of course other companies for a long time had the same problem. So they had to cope with environmental quality criteria that restricted the amount of, or the concentrations that they were allowed to emit into waters, and especially active was the copper industry at that time. And they put a lot of effort and money into developing of convincing people that these threshold criteria cannot be applied everywhere. And what they showed, or what they did, is they carried out an experiment in which they used waters from 11 different water bodies, and they added copper concentrations to it, concentration series, and determined the EC50, applying Daphnia magna, 48 hours acute test. So, and these are the EC50s that they derived. Same concentrations, or not same concentrations, but concentration range, which allowed them to calculate the EC50s, and they varied by a factor of 30. So what's probably behind that? Speciation, certainly bioavailability, the influence of environmental factors such as calcium, magnesium, pH, organic matter, etc. Probably all of it. And so they put a lot of effort into developing biotic ligand models, which was a very good idea, also from a scientific point of view. And in these biotic ligand models, you try to expose the organism to all kinds of different combinations of POC and DOC and calcium and magnesium concentrations and pH, and of course the contaminant or the chemical substance that you are interested in. And by that you will be able to account for any competition, also for ligands on, in that case, the gills of the fish as the primary uptake area, and be able to say something about bioavailability and about competition and influence of environmental constituents. And that's something, for example, that Marion has been working on for a while, and I hope she will come up with very interesting results. Speciation is certainly an issue, because we always think, and I'll get back to that in a moment, that it's the free ions which actually cause the toxicity. And when we look at this, that's just a Cheek's next speciation model taking the Rhine River, the typical Rhine River constituents into account. And what we actually see is that most of the lanthanum should precipitate as carbonate and as phosphate after can't say anything about the time frame, but eventually in the Rhine River. So only 0.02% should be dissolved or keep in the dissolved state, which would be mainly lanthanum carbonate. So do we actually expect any effect from that? And is the bioavailable fraction only the dissolved fraction? And this, and you see here, very nice, Ken Dictus, walking through the picture. These are data from Ann-Christine Heder, who did her master thesis with us, and Sebastian Höss, who is the king of nematodes in Germany, so to speak, or one of the kings. We compared here nematode tests with lanthanum, reproduction as endpoint and inhibition in % of the control in a medium without phosphate and in a medium with phosphate. And in the medium with phosphate, actually, no lanthanum should have be present as free ions at that moment anymore. But the effect response curves look very similar. The EC50 is also similar. The shape of the dose response curves is a bit different, but we still get a very high inhibition. So our idea at that time already was, is there an impact on the solid or an uptake of the solid phases by the organism who was moving on the surface, and a remobilization of the lanthanum in the gut system? And Marion will later on say more to this, and the impact of phosphate complexation has been looked into by Chantal and also by Marion. So, and then this assessment factor, as I said, was also concerned with the acute versus chronic exposure and effects, and perhaps should also distinguish that a little bit. The acute exposure is a short-term, high-dose exposure, while the chronic exposure is usually over the most part of a life cycle, and preferably also includes more generations. The acute effects appear immediately or soon after the exposure. The endpoint is often lethality. And the chronic effects appear over the life cycle, possibly over generations. Then the endpoint of chronic exposure is often immobilization or mobility, for example, immobilization for the definite. And for chronic, it's for example, root size, development, growth, reproduction rate, but also eventually mortality can be. So EC50, examples here also from the studies of Marion and Edith, I think. They come up with 30 milligrams of lanthanum per liter. And they published chronic concentrations from chronic exposures were 0.3 to 0.5 milligrams lanthanum per liter. Endpoint was mortality and published by Blenova et al. So you see the concentrations are much, much lower, and we almost get into the area of environmentally relevant concentrations. So the acute effects are relatively easy to measure. There's a clear outcome, especially if it's mortality or not mortality. While the chronic effects are more difficult, often more difficult to quantify. The response may be subtle in the lab and with a high variability, even because the organisms all have a different genetic properties, so some may be more sensitive than others. But we may have strong effects in the environment. And that's, of course, difficult to predict. So Marion's and Edith's presentation will deal with chronic exposure, for example. But these strong effects in the environment may lead to population decrease, less stress resistance, lower survival through predation, a less resilient ecosystem. So how can we actually predict that from laboratory studies? And this is difficult when you look at all the stress factors that are all the interrelationship of the definites with other organisms in the ecosystem. So these interrelationships and interdependencies, to study them in full detail is very, very difficult. And so what we look at is we narrow it down to only a few species in order to get an idea, at least in one trophic or in a number of trophic levels, what happens then. So a possibility which has been or is followed by Chantal is that she looks at nanocosms, so very small exposure units, to microcosms, and will go to mesocosms in the end. Of course, in this sequence, there's an increasing complexity, an increasing variability, decreasing reproducibility, but increasing environmental relevance. So please listen to Chantal's presentation of it. Good. So if we can summarize the challenges that we are facing, then one is to consider the impact of calcium, magnesium, pH, organic matter, etc. on bioavailability. So a helpful tool for this is the biotic ligand model, which up to now does not exist for rare earth elements. Then the knowledge on speciation in environmental samples. The speciation modeling is unfortunately not always conclusive. That's what we find. So when we model something and we get the measured concentrations, it does not always add up. And also what we expected to be measured is not necessarily measured. And we also have this organic matter problem. So organic matter is very variable in the natural system. So we have, with the modeling, we have to simplify it. A possibility would be, oops, sorry, that was much too fast. So one possibility is the DGT to apply, for example, passive sampling, or employ passive sampling for determining the truly dissolved species. And that's also something which hopefully we will still do. What about the truly dissolved free ion species and the link to bioavailability? I think Marion will get into that during her presentation. What we need to do is really investigate the link between uptake and toxicity, and study exposure and element distribution in the organisms. Exposure concentrations are often low but continuous, so we need more studies on chronic and sublethal effects. And ecotoxicological studies are important to learn about processes and modes of action, but assays provide limited information on the ecological consequences, so more COSM studies are really required. So can we measure toxicity of rare earth elements in environmental samples? First of all, it's important to be aware that there is hardly ever only one contaminant in the environment. Otherwise, it would be relatively easy. But there are many more. And the big advantage of bioassays is that they integrate positive and negative effects. So they enable us to get an impression of what the adverse impacts on the environment, on the ecosystem could be. But if we want to stick with if rare earth elements were responsible for environmental toxicity, if it would be mainly that among other metals that are there, but the rare earth element would be the ones that cause toxicity, could we identify it? There are ways we could possibly, if we had the EC50s for different biotests and a larger database on toxic effects of rare earth element contaminated environmental samples. This is work that still needs to be done. It has to be done. It has been done with other metals, where you could actually deduce from the different contamination pattern in your sample and the response of your biotests, which one of the metals would be responsible. You could also do, but that's mainly, it's difficult, I think, to differentiate between different metals. Then you can do something which is a sequential extraction, but that's mainly for organics. But can we predict the environmental risk from rare earth element containing effluents, for example? Current risk assessments are not really satisfactory, but the Panorama helps, I think, to improve this, and that is great. I think we will all, especially if you ESRs work together on this, I think we will get a big step forward, and I'm looking very much forward to that. And that's.
Thank you very much, Susanne. I don't know if there is some questions. We have some time to cover them. Oh.